Hi everyone. In this section we are going to start chapter 14, and this is on functions with multiple variables, or otherwise known as multivariable functions. So functions of several variables. As a quick motivating example, this is the kind of problem we're going to be solving later on in this chapter, but let's start with it as a motivating problem. Let's find the maximum possible product of three positive numbers whose sum is 120. So what does this mean? Well, we've got three numbers, x, y, and z, that we're trying to find, whose sum is 120. So in other words, x plus y plus z is 120. And we want to maximize their product. So I will let this function p denote their product. So p of x, y, z is x times y times z. So here I sort of naturally introduce this function which takes three input values and returns their product. This is why I've used capital P to represent the function, because I'm thinking of it as the product function. And what we'd like to do is we want to maximize this kind of function. So we've introduced a couple of things here. We've got a problem. We've converted into a question about objects in mathematics, in this case about a function. And the function is a function that has multiple inputs and a single output. Three numbers coming in, and their product is what comes out. And we want to find what combination of three numbers going in produces the maximum product. And not just any combination of three numbers, we want to make sure the three numbers going in add up to 120. So this is known as a constrained optimization problem. Optimization problem because we're trying to maximize a function, but it's constrained in that the variables x, y, and z just can't be freely chosen to be any three numbers. They've got to be restricted to this constraint. Their sum has to be 120. So this is called a constraint. And this is the multivariable function. Multivariable function we want to optimize. Optimize meaning find the maximum or minimum values. In this case we want to find the maximum. So I've sort of informally introduced this idea of a multivariable function. Let's get to the specifics of what a multivariable function is. So we can have a function of two variables. So we've already dealt with one variable. Functions of a single variable, one variable in, a number coming out. That's what we dealt with all in Calculus 1 and Calculus 2. Now we can talk about a function of two variables. So this is a function of two variables which is defined on the domain D in the plane, so the space where we could have two numbers coming from to put into the function. What is it? It's a rule that associates with each point in D, so each x, y pair in D, a unique real number denoted by, in this case, f of x comma y. So I read these round brackets of like we've done in Calculus 1. So f is our rule. It takes x, y as our input from our domain, and it produces an output. The output is denoted by f with those two numbers going into it, separated by a comma. We can do the same thing, a function of three variables. It's defined on a domain D, which is some set in space. And the function itself is a rule that associates with each point x, y, z in D a unique real number, which we denote by f of x, y, z. So a picture to sort of have in mind when we want to visualize this. This will be our picture for our function of two variables. So let's say we've got a function f x y. So xy goes in. This is the value that comes out. The value that comes out we will assign to a third variable z. What is this domain D in our picture? That's the set of all xy pairs that we can put into the function. That's going to be some set in the xy plane. So I'm sort of thinking this green blob as the set of all pairs of points x and y. So this is our set D, and it's in the xy plane. For each point in D, let me just pick a arbitrary point in D. What we do is we fire it into our function. We evaluate f at that point x comma y. It produces a third number, this number z, and that's the number we notch off on our vertical axes. So maybe that number that comes out has some height here, which we'll call f of, if I call this point, let's just say it's arbitrary point a comma b, then this is f of a comma b is the height of that point. And we do this for all values in our input set, in our set D. And what we end up constructing is some kind of surface. Maybe it looks something like this. And we've got something that looks like this kind of sort of, I don't know, like a mountain kind of shaped region. And the idea was for each point in our domain, we can evaluate our function at that point, and we get a point in space whose x and y values were the input and whose output was that z value. So what I've essentially introduced here is not only in the definition what a function of two variables is in this case, but also how we are going to visualize these things in terms of their graphs. So this is a graph of z equals f of x comma y. That's our graph of our function. And that green section is the domain. So let's look at some examples. So we've got a function, f of xy, function of two variables. It's defined to be the square root of x squared plus y squared minus 16. Is it possible to evaluate f of 2 comma 1? Well, let's see. 2 comma 1, that means we are plugging in to our expression for f. We are plugging in the value of 2 for the x variable and the value of 1 for the y variable. So this would be 2 squared plus 1 squared minus 16, or that would be square root of 5 minus 16, or the square root of negative 11. Now in this course we only deal with real numbers. We're not dealing with complex numbers. If you know about those, just to be reassured, we're not dealing with them in this course. If you don't know about complex numbers, not to worry, we're not dealing with them in this course. But the issue here is what is the square root of negative 11? What real number, when you square it, is going to be negative 11? And the answer is there is no real number whose square is negative 11, because the square of any real number is non-negative. So is it possible to evaluate f of 2 comma 1? Well, when we plug it in, we get that this is, maybe I should say, this is not defined or not a real number. Not a real number. So we can't evaluate f at 2 comma 1. It doesn't make sense to plug that in because what we get out is something that isn't a real number, something we can't define. Alright, so that means that 2 comma 1 is not in the domain of f. The domain of f would be the set of all things we can plug into it, and it will make sense to evaluate, but we can't plug 2, 1 into it because what comes out is not a real number. So that's not in the domain. Let's have a look at some other ones. F of 5, 0. F of 5, 0 is the square root of 5 squared plus 0 squared minus 16. So that's the square root of 25 minus 16. That's the square root of 9, which is 3. So that's fine. 5, 0 can be plugged in. We get a value of 3 out. I just want to point out that the value is not plus or minus 3 that comes out. This is a square root function, and it's extracting the positive root because, well, there's no negative sign in front of it. This is the positive square root function. There's going to be a unique value that comes out. So when I have this expression, square root of 9, means I'm taking the positive square root, or the value of 3. What's f of 10, 10? Well, that would be the square root of 10 squared, 100, plus 100, minus 16. So that's the square root of 200 minus 16, so that's 184. And so there's our value, square root of 184. That's an exact answer. If you wanted to simplify it a little bit, maybe you could look for a perfect square inside of it and extract that out, or if you were looking for a calculator, a decimal answer, you could evaluate it on your calculator. But we're completely fine with this calculator ready form because that's the exact answer for that function value. We're asked to find the domain of f. So what is the domain? The domain of f is the set of all values of x and y that makes sense to plug into it. So in the absence of actually having the domain specified for us, saying here's a function, this is the domain, if the domain is not specified, then we just assume it to be as big as possible. All the possible xy value pairs that make sense to plug in is what we're going to take to be the domain. So if I'm thinking of it that way, the domain is going to consist of all the xy pairs such that x squared plus y squared minus 16 makes sense to have under the square root sign, that I have no problems with dealing with the square root of this. Well, that means I need this to be positive. Or in other words, I need x squared plus y squared to be greater than or equal to 16. So that's telling me that my domain is consisting of all points in the plane that are outside a circle of radius 4. So here's my xy plane. Here's my circle of radius 4. Put a little 4 here to indicate that. And the domain is going to consist of all the points outside. So I'll shade that in. That's our domain. So we've got the domain of f is, it's the set of all points x comma y in R2 such that x squared plus y squared is greater than or equal to 16. And now we can see why the 2, 1 didn't work. For example, 2, 1 wasn't in the domain because it's somewhere around here. Maybe I'll zoom in so we can see. So if that's 4, then 2's somewhere around here, and then up 1 unit. So there's our point 2, comma 1. And it's inside the circle, and that's not in the domain of our function f. Let's look at this next problem. So we're looking at this function here, g of x, y, z. Now it's a function of 3 variables, and we want to find the domain of g. What is the domain? Well, the domain of g, it consists of the set of all points x with components x, y, z that is in R3 such that we want it to make sense to plug in to our function. Well, when I plug it in, I get the square root of x up top. Oh, that means I need x to be bigger or equal to 0 in order to be able to square root it. But I also need to be able to square root the sum of y and z. So I need y plus z to be bigger than, in order to square root it, I need it to be bigger than or equal to 0. But it's also in the denominator. So I'm going to also have to divide by it, which means I can't have it being 0 because I can't divide by 0. So I need it to be strictly greater than 0. So notice the subtlety here is we have equality and no equality here. Denominator can't be 0, but the numerator could be. So there's our domain. And now what we'd like to do is evaluate our function at 16, 50, and 50. Now as a quick check, we could say, is that in the domain? Well, x is bigger than 0, and the sum of y and z is bigger than 0. So yeah, it's in the domain. Let's see what it works out to be. This is the square root of 16 over the square root of 50 plus 50. Square root of 16 is 4. Square root of 50 plus 50, that's 100. Square root of 100 is 10. So 4/10, or we could simplify it, 2/5. So 2/5 is the value of our function g at that input 16, 50, 50. Now at this point you may be thinking, well, when would I ever encounter functions of 3 variables, for instance? Well, I mean, we could be interested, for example, in the temperature at a point in space. So to define a point in space, we would use 3 variables. To identify that point in space, we've got some x-coordinate, some y-coordinate, some z-coordinate. We plug that into our temperature function, and it produces a value, the temperature at that point. And that is a function of 3 variables because it's depending on your point in space, which is given by 3 coordinates. But with that in mind, you can think of higher dimensional functions, so functions that have more variables in them. Maybe I'm interested in a function which records not only the temperature at that point, but also at a given time. So it's a function of the x-coordinate, the y-coordinate, and the z-coordinate, the point in space, but also of a variable t, because temperature is going to vary over time. So I've got 4 input variables, and then my temperature function returns a 5th number. And so if I was to think about graphing that, I'd have 5 components, 4 inputs, and then the 5th output. And so thinking about a graph of that, that would be a graph in 5-dimensional space. So we can very easily construct functions with multiple variables that make sense to us, that are familiar to us, just given some physical context. And what we're doing in this course is we are looking at ways to analyze and understand these kinds of functions. So let's sketch a graph now. So we're going to sketch the graph of this function f. It's a function of 2 variables, x and y. So what is our graph going to be? Well, I'll write it down once here. What is a graph? A graph is really just the set of all points which consist of components where we've got the inputs listed out. So here's a point x, y, and then the output is attached to that as well. So that's our 3rd variable, z. So we've got our 2 input variables and our output variable, and we're sketching that as a point in 3-dimensional space. We want our 3rd variable to be equal to the function value obtained from our first 2 variables. So we're looking at sketching the set of all points with x and y components, and then the z component is what we got from the function being evaluated at the x and y components. So in other words, it's the set of all points x, y, or set of all points with components x, y, and z in R3, such that z is equal to x plus y plus 2. If we look at it in a slightly different way, rearranging that equation, that gives us the condition on what our components of our point have to satisfy. This is saying that it's x plus y minus z equals -2. So I've just rearranged some of the variables. So again, what is a graph? A graph is the set of all points. So it's a function of 2 variables. So it's the set of all points in 3 dimensions, which the first 2 components are the inputs, and the 3rd component is the output of our function. In this particular case, we see that it's a set of all x, y, z triples that satisfy this equation. And we already know from a previous section that this is the equation of a plane in 3-dimensional space. So the graph of this function is a plane. How am I going to draw this plane? Well, what I'm going to do is I'm just going to rotate my axes just a little bit. So I'm going to let x go off to the right, I'm going to let y go into the page, and z go up. All I've done is slightly rotate the usual way I've been drawing the axes, but you can see that they're all properly positioned because of the right-hand rule. If I put my fingers in the x direction, curl them in the y direction, my thumb points in the z direction. Why have I slightly tilted them like this? Because in order to get the sketch of this graph, I'm going to do what essentially we did when we first started sketching graphs in high school for functions of a single variable. We just collect some points on them. Collect some points together. See what kind of points we have on this. this graph. And so what kind of points do we have? Well, I'll list them down here. Here are some points. I'm going to let y be 0 and z be 0, and I'm going to look at the point where this graph will intersect the x-axis. So if I look at the equation, set y is 0, z is 0, that gives me x equals -2. So there's a point on it. So that means we got a point out here. That's -2, 0, 0. What's another point? So that's one point. What's another point? I'm going to do the same thing. Maybe I'll take x and z to be 0, and I'll see where it hits the y-axis. So with x being 0 and z being 0, I look at my equation for the plane. That gives me that y is equal to -2. Okay, so there's a point. Maybe I'll put some notches there. There's another point on it. Oh, sorry, it's -2. So I've drawn the y going off into the page. So the negative is out front. That's really the y I've drawn my coordinates this way, my coordinate axes this way, is because I want all the action to be out front. I just want to sketch it so all the stuff that I'm plotting is out front on these coordinate axes. So that's going to be 0, -2, 0. And lastly, with x is 0 and y is 0, the z value has to be 2 in order to satisfy the equation. So we're up here at 2, 0, 0. Why did I pick 3 points? Well, I know the graph is a plane. It takes 3 points to determine a plane. I've got 3 points plotted now, so I know that these 3 points are going to define that plane that is the graph. So now I just need to sketch the plane in there. Maybe I'll sketch it in green. How can I sketch the plane? Well, first maybe I'll start with a triangle, because I can connect those up with a triangle. And that triangle has to live on the plane. And so I just need to draw my plane so it contains this triangle. And so maybe my plane, it's just going to be a portion of the plane. I can't draw the whole thing, but it's going to look like this. It's going to pass through these points, and maybe it'll look something like this. So there's my plane, and I'll continue these lines on. So there's my graph. I've got 3 points, so that's enough to determine it. If my picture doesn't kind of look like a plane, if you have a hard time envisioning it, it's all right, because I've got the 3 points there, they specify it. The other thing we could do is we could say this is a plane. We know 3 points. In fact, we know 1 point then, because I've already listed the 3 points, so we know 1 point on it. Sorry, I wrote 2, 0, 0 up there. I see that I've made a mistake. It should be 0, 0, 2. That's the point on the z-axis that we wanted. So there's our point. I'll write that one down, 0, 0, 2. And a normal. The normal we can read right off from the equation. So the normal would be 1, 1, -1. So there's something else we could use to get a feel for what this plane is. It passes through the point 0, 0, 2, and it's got a normal vector of 1, 1, -1. All right, so that's our first attempt at sketching graphs. Let's go ahead and look at the next example. We're going to sketch the graph of this function. Again, it's got 2 inputs, 1 output, so the graph is going to live in 3 dimensions. And what does it look like? Well, the graph is going to consist of all points x, y, and z that satisfy this equation. So x, y, and z have to satisfy that equation. I'm just going to rearrange this equation a little bit to see if I can get a feel for what this object is. So I can square both sides. 36 minus 4x squared minus 9y squared. I can push everything involving the variables to one side. So 4x squared plus 9y squared plus z squared is equal to 36. I could divide by 36 to make a 1 over on this side. Might not be too clear why I'm doing this. Maybe once I do it, we can start to see why it seems reasonable. So I get to here. And so the set of x, y, z values that live on my function, they've also got to live on this curve, or this surface, or They've got to satisfy this equation, is really what I want to say. One further thing to observe is that from this step here, we've just said, okay, let z be the output variable. Then, because the function value is taking the positive square root of 36 minus 4x squared minus 9y squared, we have that z has to be positive. So z has to be positive here, or at least bigger than or equal to 0. It's got to be non-negative. And so we're interested in the set of all x, y, z pair or triples that satisfy this last equation where the z value is bigger than 0. And now we have to think, what kind of object is this? What does this look like? What kind of surface is this? Now we would have studied these kinds of equations in 12.6, but we've deferred that section to a little bit later, a couple of lectures from now, so we'll come back to that. So it's all right if we're looking at this going, I still don't know what that is. Just imagine, though, if I got rid of the denominators, the 9, the 4, and the 36, and instead my expression was just x squared plus y squared plus z squared is equal to 1. So recall, x squared plus y squared plus z squared equal to 1 is a what kind of object? A sphere. It is a sphere. So that we got when we studied the distance formula for points in space. We introduced the idea of a sphere. So this is not a sphere because we've got these denominators. But what do those denominators 9, 4, and 36 do? They actually just stretch the sphere in the different directions by different magnitudes. So what we actually get here is like a stretched sphere. It's stretched differently in the different directions. And that's known as an ellipsoid. But we'll get the sketch of it here. So how can we get a good graph of this? Well, the idea is we plot some points. We know it's got to be kind of a sphere-like object. There's just some stretching that's going to happen. So maybe I'll make my z-axis a little bit longer. So again, I'll think of some points. What are some points on this object? What are some points that satisfy the equation? Well, I could figure out where they intersect the axes again. So where does it intersect the x-axis? That would be where y and z are both 0. Where y and z are both 0. So maybe I'll get rid of that and just explicitly write that down. When y equals 0 and z equals 0, what we get is x squared over 9 is 1. So x squared is equal to 9. Or in other words, x is plus or minus 3. So we have that. It has that point there, which is 3, 0, 0 on it, and then also one back here, which is negative 3, 0, 0 on it. What are some other points we have? So there's our first collection of points. We can do the same thing for the y-axis. So that would be x equals 0 and z equals 0. That would mean that y squared over 4 is equal to 1, or y is equal to plus or minus 2. So we've got that passes through that point there, which is 0, 2, 0. And it passes through this point here, which is 0, negative 2, 0. And lastly, what about when it hits the z-axis? This is when x is 0 and y is 0. And so that means we have z squared over 36 is 1, or z squared is equal to 36. So z is equal to just 6, not negative 36. Why is that? Because z is positive. Z is positive. Z is the value that's coming out of the function, and at the very top of the page, the values that come out are the positive square roots. So right down here, we've got just z is 6 that's coming out. So we've got I'll change my color again. 1, 2, 3, 4, 5, and 6. 0, 0, 6. So those are some points we know. We also know this is kind of a sphere-like object, so we can connect all of these things up in what would potentially be a sphere-like kind of object, and it would look something like this. And so I kind of maybe like a football cut in half, sort of half a football is what we're looking at here. So this sort of a stretched out kind of thing. Well, it's actually vertically now. So stretched out. It's stretched out by a factor of 6 along the x-axis, by a factor of 2 along the y-axis, but by a factor of 3 along the x-axis. And this is known as an ellipsoid, or at least half of one. It's half of one, half of an ellipsoid. It's the upper ellipsoid, if you want to think about it that way. So there's another way we can graph a kind of function. If we recognize it and are able to piece together the individual pieces that allow us to figure out what the sketch looks like. It's sphere-like, but it was stretched, so we graphed this. In section 12.6, we do introduce a lot of these things, ellipsoids, paraboloids, hyperboloids, and we talk a lot about those and look at their graphs. But those are very specialty type shapes. In this section, we are just looking at graphing in general. Okay. The next thing is, well, maybe I'll keep that picture in mind. The next thing is it is difficult to try to figure out what these things look like in 3 dimensions. This is where graphing utilities or software helps immensely. You can just plop these things into a graphing package and boom, it shows you the image and you can drag it around. So that's where math3d.org comes in. You know, we can plot on math3d.org. Very nice website where you can just open it up and you've got access to just plug these things in and look at their graphs and drag them around. Another way we can visualize these kinds of surfaces, the graphs of these functions, is by projecting them in some sense, looking at slices of them in lower dimensions. So I've got a 3-dimensional object. I could slice it up and look at the cross sections in 2 dimensions. So these would be known as the contours or level curves. And I'll just explain the difference between contour and a level curve in a second. But here's the general idea. We've got some surface. Maybe it looks something like this. And I'll just give it some perspective. So we've got some surface, enough reference lines in here so you can sort of see the 3-dimensional nature of it. So we've got that surface, kind of like maybe a lake bed with various depths going across this lake. And we've got our coordinate system somewhere in the background here. So there's X, here's Y, and here's Z. And what we could do is we could imagine slicing this surface in a given direction. In this particular case, we're going to slice it by a plane parallel to the XY plane, so a plane at a given height Z. So let's pick a height. Maybe I'll pick a height right about here. And so if that's my height, we'll call it Z equals K, so I'll notch that off as a K there. And then what I'm going to do is I'm going to take a plane at that height, and I'm going to let that plane slice across my surface here. So it looks something like this. It'll be solid because it's out front. And then where it's hitting it, maybe it's hitting it somewhere around here. And maybe something like that. So this plane has just sliced through our surface, and where it slices it, it's made these 2 kind of circular type curves. These 2 curves that we get. It could be 2 curves, it could be 1, it could be none. It all depends on where we cut it. If I cut it a little bit lower, I would have missed that thing on the right, but I would have captured sort of one circle on the left. Or if I sliced it even higher, maybe I get one giant sort of circular type shape because I'm slicing it at a point where I've missed both of those sort of dips down. And the point is that I've sliced it at some level and it produces some curves. These are called contour curves. And they are at a particular height. So they are contour curves. We could say at height k, or I could say for z equals k. So these are the contours for z equals k. When we get our contour curves, maybe I'll draw another one in here. I'll get a contour curve at a different height. Maybe I'll say this is going to be k2. So I do another slice, and what I end up with is getting something that looks like this. This is the contour curve for z equals k1. And I can take these contour curves, because now they're just curves, they're just plane curves, they live in a plane. And I can just drop them, or if this was for negative z values, move them up. So in other words, just project them onto the xy plane. And when I do that, what I end up is getting, that first one is sort of looking like this, with that second half of it over there. And then I get that green one that's sort of around both of them, like this. So now the point is that these ones I've drawn down below, they live in the xy plane. So these are just curves in 2 dimensions, in xy plane, things we're used to sketching from Calculus 1. When we do that projection down here, these are known as level curves. So the contour curves are up, drawn actually on the surface themselves in 3 dimensions. When you drop them and squish them down, so sandwich them all onto the plane, they're called level curves. And we would label them. A level curve corresponding to level K2. These are the level curves corresponding to level K. And the idea is that these level curves carry information about the shape of the surface. And so sometimes we can look at level curve diagrams instead of having to look at the attempted drawing of a 3-dimensional surface. We could look at the level curve drawings, which are these plane curves, these curves in 2 dimensions, and see how the surface is constructed from these level curves. So let's get an example where we sketch some typical level curves of some functions. So here I've got the function f of xy is equal to x squared plus y squared. And then on the other hand, we're going to also look at g of xz is equal to the square root of x squared plus z squared. So our function f, we want to sketch some typical level curves. So what we want to do is we want to say, okay, level curves. We're going to take our output of our function, so in this case our output is f of xy, and we're going to set it equal to k, for some k. So we're set it equal to a constant. And let's figure out what are the set of all xy values that when you plug in, they produce the exact same output. In this case, it's k. So this is the equation we get. And what we can see is that this is a circle of radius root k. So what that means is, if I draw our level curves for various values of k, I can maybe get a feel for what the 3-dimensional shape looks like by looking at these 2-dimensional cross sections called the level curves. So let's see, what does it look like? Well, we'll just label them. When k is 0, that would be a circle of radius 0, so that would be a dot. So maybe I'll label that. K is equal to 0. What about when k is 1? Well, k is 1, I get a circle of radius 1. So then I draw that one in here. So this is k is equal to 1. When k is equal to 2, I get a circle of radius 2. root 2, a circle of radius root 2. So it'd be something like this. I'm going to change the color of this one just because I don't want those k values to start confusing as to which one they are pointing to. So k1 is that outer green one. This is k equals 2, and it's a circle of radius root 2. And then we can keep going. What about if k is 4? Well, that would give me a circle of radius 2. So maybe we'll draw one more in here. There's another circle. That would be radius 2, and that would be our k equals 4. So what I get from this picture is that as my k value increases, as my z value increases, these are the cross sections. So if I imagine looking down on it and it coming out of the page at me, where I move the corresponding circle to the height in the z-axis, which I imagine coming out of the plane, I can see that each of these bigger circles is moving further up and up and up. So what I get is this sort of bowl shape opening up, where each circle, the bigger the circle is of radius is, the higher it is moved up the z-axis. So that's the kind of information I can see from this. It's kind of a bowl shape opening upwards. We can do the same thing for this one. Level curves. We're going to let k be our constant value. In this case, the missing value is y. So that would be x squared plus z squared is equal to k. And then I can clear the square root and get this. And with this one, this is a circle of radius. In this case, it's of radius k. So when I sketch it out, it's sort of the same feel here, where that's a k equals 0. When k equals 1, we get a circle of radius 1. So maybe that's a k equals 1. And then when k equals 2, I'll try to keep my coloring the same. When k equals 2, we get a circle of radius 2. And then when k equals 4, we get a circle of radius 4, so I get one that's much bigger than I had over on that other one. So that's 4, that's k equals 4. Okay, so the idea is the k value is, again, where this circle is really going to sit as a contour curve, as a cross-section. So k equals 4 would be sitting at a height of z equals 4, but it's a really big circle. It's a circle of radius 4, whereas in the other diagram, it was a circle of radius 2. So if I was to sort of compare these two sketches involving level curves and try to think of what they tell me about the surface itself, it looks like the one on the left is a little bit more narrow as you go up, because at a given height, at height 4, for example, the circle is radius 2. Whereas on the other one, at height 4, your circle is radius 4. So it looks like the one on the right is much wider. It opens much wider as you go up the z-axis. So even though their cross-sections are circles, we're still getting information about how wide the circle is, or how big the radius is at a given height. So that's the idea with, we take these three-dimensional objects and we try to draw them in 2 dimensions, where we can infer the information that we've got from that 2 dimensions as to what it's telling us about, or infer from that information what it tells us about how it looks in 3 dimensions. You might say, well, why don't we just sketch the 3-dimensional graph? Well, the reason is now you can maybe imagine going further. Suppose I have a function of 3 variables, f of x, y, z, and I'd like to know what its graph looks like. Well, that would involve 3 inputs, 1 output. The graph would live in 4 dimensions. We just can't visualize that. But what we can do is visualize the level surfaces. So for what inputs x, y, and z do they give the same output? And then I can sketch those graphs for varying different outputs. Kind of like we got here, we can kind of infer that the shape looks like a bowl, kind of opening upwards. Whereas with this object, we might be able to get a feel for what its graph looks like. And so let's see if we can do that. Describe the level surfaces of this function. So what we're going to do is we're going to, our output variable, we're going to fix it to be a constant. We're going to say it's constant k. So that's x squared plus y squared minus z. I'll rearrange this a little bit. That's x squared, well, maybe I'll push the z to one side. This is z is equal to x squared plus y squared minus k. And let's see, did I get that fine? That all looks good. And now what we want to do is get a feel for what this thing looks like. So what does this look like? This is for a given k value. So what we're going to start with is maybe a shape like k equals 0. So kind of like what we did above. When k equals 0, what does it look like? Well, when k equals 0, we get z equals x squared plus y squared. What does z equals x squared plus y squared look like? Well, z equals x squared is like a parabola, so maybe I'll sketch that in first. So it looks like x, y, z. We're looking at k equals 0. I'll put this in green. When this z equals x squared plus y squared intersects the xz plane, the y value is 0. So that's like a z equals x squared. So that's like a parabola opening up. That's sort of living in this xz plane. And it would also go up in the other direction as well. So it sort of go over to there. But then I can see, how does it intersect the yz plane? Well, that would be z equals y squared. So there's sort of a parabola opening up here as well. So it's kind of looking like maybe something like this. And I'm just going to try to connect them up to see if we can get a feel for what this shape looks like. I'll get rid of some of these reference lines. And I'll get rid of some of this scribbling going on over there. And so the idea is, I'm going to try to redraw it a little bit so that it looks a bit better. Kind of looks like this, where we've got this sort of bowl kind of shape opening up. Maybe I'll make this one go a little bit further and then sort of draw these things around. There we go. Maybe that's probably a better look to it. So it's kind of this bowl-shaped thing opening up. That's our z equals x squared plus y squared. This is known as a paraboloid, and we will come back and look at these and their sketches and whatnot in 12.6. But for right now, we're just getting a feel for how these apply in this situation. So that's the level surface when k is 0. But what about when k is 1? Well, that'll be z is equal to x squared plus y squared minus 1. So that's a paraboloid where the z value is basically shifting things down. So minus 1. So it's going to look like the same thing, only it's going to be down 1 unit. So it's going to look something like this. I'm going to just fix that side because maybe it's going to sort of engulf it. So that's z equals x squared plus y squared minus 1. So this is when k is equal to k is equal to 1. And this one was when the green one was when the level surface when k is equal to 0. And we could keep doing this. We could keep looking at different k values. When k is equal to 2, that's going to give us another paraboloid, sort of down here a little bit more, opening up. And so that's k is equal to 2. And so what we are imagining is that this four-dimensional graph, this graph of this object in 4 dimensions, is kind of made up of these paraboloids nested in each other, but each paraboloid is moved in the fourth dimension along its axes by 2 units, 1 unit, 0 units. Much like up here, these circles are moved along their third dimension by whatever their k value is. So this is a bit of a mind twister. I mean, we're trying to visualize in the fourth dimension after all, but this is how we can gather some information about functions of three variables with one out, which are essentially their graphs, are four-dimensional objects. This is how we can look at slices of them in 3 dimensions. So it's somehow, this is a four-dimensional object that's made, it's like an onion made up of these paraboloids sort of wrapping in around each other. All right, let's have a look at the last example. We want to verify that the contours of this surface, z equals sine of the square root of x squared plus y squared, are circles. And then you can use that to convince yourself that the graph is as we've shown. So I've sketched the graph here of z equals sine of the square root of x squared plus y squared. And you can see down, well, on the object itself, you can see the contour curves, but you can also see down in the plane below the level curves. And actually, I should be specific. These level curves, I've even moved them further because you can see where the 0 is. The 0 is here. So these level curves, if they were to live in the x, y plane, they should be somewhere in the middle because this surface is oscillating about the origin. But I've just pushed everything down below the surface so that you get a clearer picture of what the contour curves are. They're circles. And we just want to verify that they are circles. So how do we get that? Well, the way we get our level curves is we take our function, we set it equal to k, where k is our arbitrary constant, the height that we're going to slice this thing at. And when we do this slice, we get an expression that looks like this. And now what I'd like to do is I'd like to try to get this in a form that I can see is a circle. So the thing to observe at this point is that k is any value. K can be any real number. So I'm looking for the value of this angle, so square root of x squared plus y squared, the thing I'm putting into the argument for sine. I want to know what value that has to be so that sine of it is k. Now this takes a little bit of thought. Ideally, we'd like to just say, oh, well, that means square root of x squared plus y squared is arc sine of k. But that's not quite true, because arc sine of k requires, well, think about it, sine of this thing is going to be equal to a number between plus or minus 1. And so k can only be a value between plus or minus 1. And so I'd like to take arc sine of that, but I'm going to have to get a lot of circles out of this. So we have to be really careful how we think about this. So here's what I want you to imagine. I've got a sine function drawn. And I'm interested in, right now I've got sine of something equals k. So I've got some height k that I've just sliced it at. So that's the height k. And now I'm asking you, what angle do I plug in for sine that gives me k as an output? Well, there's lots of angles that I can, in fact, there are infinitely many. These are all the different values. All these spots along the x-axis, or this horizontal axis, are going to give me values of k that come out of sine. This is the sine function, so maybe I'll put an x and a y here, and this is y equals sine of x. So I have to take that into mind. Can I find one value, one angle? Absolutely. This one right there is called arc sine of k. That's the one that's between negative pi by 2 and pi by 2. So that's pi by 2 and negative pi by 2. So arc sine of k is the specific value that's between pi by 2 and negative pi by 2. So we can get one value. And then I have to think about how can I get all the other ones. Well, I can get other ones by taking whatever that value is, and I can get this one over here by adding 2 pi to it, so plus 2 pi. And I can get the next one way over there by adding 4 pi and so on, or I could get this one back here by taking arcsine of k and subtracting 2 pi from it. So I'm just going to jump from this one to this one by subtracting 2 pi. So I get half of them in this way. Maybe I'll color code these. I get all those green ones, but now I also want to get the blue ones here, which I'll put here in blue. I want to get these values as well. So how do I get those values? Well, here's where another picture comes in handy. So I'm refreshing your memory with all the unit circle and trigonometry that you would have seen a bunch of times, but it's good to see it again. So again, what I'm interested in is I've got my unit circle diagram drawn here. The idea is if I've got an angle theta, then the height of that point, the height of that point there, or its coordinates are going to be cos, x coordinate is cos theta, the y coordinate is sine theta. So in other words, the height is sine theta. So that's what that is. That's sine theta. And the idea is I'm trying to say, well, I've got a height of k. So I'm slicing it at some height k. And I want to know what are the two angles that give me that height of k. One of them is that angle right there, that theta. That one, the one that's between 0 and pi, or negative pi, sorry, 0 and pi by 2, or in other words, negative pi by 2 and pi by 2 in case it was on down below in the negative y values. This one is arcsine. That's the definition of arcsine of k. But then I need to find this angle over here, and I'll write that one in blue. I need to find this angle as well. How do I get that one? Well, it's a little bit easier to see from this diagram, because that is going to be that angle theta, that same angle theta, or arcsine of k. So that blue angle there is pi minus that angle theta, which is arcsine. Arcsine. For some reason my pen just stopped working. Arcsine of k. So that's that blue angle, or in other words, the pi minus arcsine of k. That's this guy right here. Pi minus arcsine of k. So that's another angle, and those are the two angles we want. And then 2 pi plus any of those also gives us another angle. So all of that discussion was to really just say that the square root of x squared plus y squared is equal to arcsine of k plus any multiple of pi, so we'll say 2 pi n, or the square root of x squared plus y squared is equal to, so that first one uses that angle, or it's this angle that's in between 0 and pi by 2, or negative pi by 2 to pi by 2 if we were below. This next one is this angle. So pi minus arcsine of k plus 2 pi n, where n can be any integer. And we can rewrite this as 2n plus 1 pi, because there's a pi plus an even multiple of pi, so it should be an odd multiple of pi minus arcsine of k. And so these are our two different expressions we get for our level curve, so the two different kinds of curves. Again, the first one is going to be x squared plus y squared is equal to arcsine of k plus 2 pi n squared, or x squared plus y squared is equal to negative arcsine of k plus 2n plus 1 pi all squared. And so these are circles. And those are the circles that we're getting in this diagram here. Those are the circles that we're getting. Those are our level curves. And so this object is made up of a bunch of these circles, sort of moved up to various heights depending on the value of k and they are producing this sort of wavy type structure, like you throw a pebble in a pond and these are like waves rippling out, and that's our ultimate shape of the graph. All right, so that's it for this section. Thanks for watching.